Okay, so we are here now. What we're going to do is use both VS Code as well as our notebook to be able to see what's happening at every step. The first thing that we're going to do is open the detect notebook. So we are here. If you skip the setup, feel free to watch the video that I put. We're going to start with loading the model that is already stored locally in our Google Drive. So let's run this. And then we're going to import our PyTorch model. If I scroll to the top, you see that CKPT is this dictionary in a similar way as we did here, torch.load, and then the model. And then in the next line, CKPT became CKPT model. We override CKPT with the value inside CKPT model, which is the detection model. And then here we send it to the device, and then we convert it to float 32. We won't be sending it to the device in our Colab environment, but we are going to convert it to float 32. So now CKPT is our detection model. Now we're ready to step into the fuse convolution and batch normalization. So here we're saying that if fuse is true, which it is, and has attribute fuse, which it does, if we go to function variables, fuse is right here. And the reason fuse is right here is because we are inside self. CKPT is the detection model, which inherits from base model. And you can see here, base model has a function called fuse. So given that this is true, both these are true, we're going to call CKPT.fuse.eval. Eval is because we're doing predictions and we don't need the model to calculate any gradients as we would do if we were training. So when we step into this function, we jump right into the fuse function inside the base model class. Here we're just going to print fusion layers in the terminal. And now we're going to do a parallel path between VS Code and what we have in our Colab environment. So CKPT, we're going to rename it or assign it to the variable self. CKPT, detection model, became self right here. So we're going to follow the same terminology. So this is nothing new. We just created another variable called self, which has the same values as CKPT. We are doing this so that we can run the same code that you see here in our Colab environment. Now, before I step into this, I want to show you what self.model actually has. So given that detection model is self, if I call self.model, I'm going to be inside here in the sequential of all different modules within the neural net. Notice that we are not in detection model anymore. Now we are inside sequential. And this is exactly what this is doing. It's saying within the detection model, call the model. So we are in sequential in the same way that here, we would be right here, and then iterate over all the modules and tell me as you're iterating, is part of conv or dw.conv. We're not using dw.conv in this architecture, so we'll focus on conv. And indeed, some modules are definitely conv. They have the conv class, not just here, but all the modules here also have the conv class, like C3 and others. Now, in order to replicate this in our Colab environment, we have to perform some imports. So for example, you see that conv is imported here at the top. From models.common, we're importing these classes, models.common, which we can see it right here as well. And there's a number of classes that we do want to import, like conv, C3, and so forth, essentially the ones that we have in our architecture. So we don't need to import all the other classes that we are not using, but definitely the ones that we're using, we need them. So in order to replicate in our Colab environment, we are performing some imports. Remember that everything is downloaded in our Google Drive, and we did that right here at the top on our setup video. Now let me run this function first and then talk about it. So here we are iterating over all the modules inside sequential. And we're saying if we have the class conv and that has an attribute batch norm, then print it here. We're also counting the number of modules. If I scroll here to the top, the first convolution, which is this one right here, has input channels 3, output channel 64, kernel size 6x6, 2x2, stride, padding as well. and it also has a batch normalization layer with the corresponding parameters and an activation layer. Now we can also count the number of conv classes that we have in our neural network. In our case is 101. We can also double check that this is correct. So here we have 1, 1, 9, 1, 15. These, for example, just so that you know, there is 2 convs inside each bottleneck. So 6 times 2, that's 12, 13, 14, 15. There's 1 here, there's 21 here, 1 here, 9 here, 1 here, and another 1 here. The backbone has 61 conv classes, and then the head has 1 and 9 here, 1 and 9 here, so that is 20. And then here we have 1 and then 9, and 1 and then 9, also 20. So 20 plus 20, 40 plus 61, 101 conv classes. We can also get a deeper look at the conv class inside common.py. This class gets initialized, and then here we have the forward pass, which consists of a convolutional layer, self.conv, which is an instance of nn.conv2d, and then this is the input to the batch norm layer, which is an instance of nn.batchnorm2d, and then this is the input to the activation function, which in this case is Silu. You can also read more about these classes on the PyTorch documentation. This is the conv2d, batchnorm2d, and the Silu activation function. Now, for example, if we focus on the first conv class, here I'm just looking for the first one and then breaking out of the for loop. And then here, m is this class. So if we call m.conv, we expect this as the output. And in the same way, m.bn, we would expect this as the output. Now let's do the same in our VS environment. So you see m just became conv, and this is going to be true since m is a conv class and also has the attribute bn right here. So we're going to step into this, and then m.conv right here, as well as m.bn right here, are going to be inputs into the fuse, conv, and batch norm function. And now we're in torch utils inside the fuse, conv, and batch norm function. Now, to be able to have the same nomenclature, m.conv and m.bn became conv and bn, and these will be used as the arguments to the variables here. So we are going to rename it in our Colab environment as well. So we'll just rename them, or actually create another variable called conv and batch norm. So we can actually see here the values of the arguments that we are going to provide to this new convolutional layer. Our inputs are 3 RGB, our outputs are 64 for this layer, and then the value of the kernel, stride, padding, etc. Again, we are focusing on this first layer. So when I start running this, the values that we have from conv will be inputs to this fuse conv convolutional layer. Now we're gonna set gradients to false because, again, we're doing prediction. We don't need to calculate the gradients. And then in this case, we'll set it to our device, which is CPU. So when I run this, we're gonna see the fuse conv variable created here that contains the inputs from our conv layer. An important note here, for this fuse conv, we're setting our bias to true. The bias of the conv class was actually set to false right here. So the convolution of the conv class only contained the weights and not the bias terms. But in this case, we do want to add the bias because we are going to fuse the convolution and the batch norm. And while the convolution has the bias term set to none, because it was initialized as false, our batch norm layer does have a bias term. So the convolution has the weights, and the batch norm has both the weights as well as the bias term. So when we run this, fuse conv has been created with the values from conv and also adding this bias term at the end. So let's do the same in our Colab environment.